Welcome back to Physics 141 Online. I'd like to work out a simple example problem that's not too different from some of the homework problems that you're working on the topic of rotational motion, and specifically static equilibrium. You'll see that the question involves a solid beam that's hanging over the edge of a tall building. And if we know the mass and length, and we know that the beam is lying so that 1/3 of its length hangs over the edge of the building, we'd like to know what's the maximum mass that can safely be added to the very end of the beam. Of course, if the mass exceeds this maximum safe amount, then the beam will begin to rotate and will slide off the building. That's not very safe. So the first thing that we can do is identify that this type of problem, just knowing what the picture is going to look like, is a problem that it deals with rotational equilibrium or static equilibrium. So what that means is, then as we draw a sketch and develop a solution, we will be using Newton's second law for rotational motion. So here is the sketch. Alright, so here's the edge of the building, and what we've got is a beam. Boy, that's really not a very good beam. Let's see if I can do a better job of drawing a straight line. Apparently, it's not as easy as it looks. So there's a beam where, take my word for it, 1/3 of the beam is hanging over the edge. So what we've got here is a distance L/3. The beam itself is a mass m and has a length L. So of course this distance here is 2/3 L, if that becomes necessary to use. And what we're going to do with this beam, and I'll just draw in a little bit of shading so that we realize that it's a solid beam, we're going to load it by putting an additional mass right at the very end. And of course, if that's a very lightweight mass compared to the mass of the beam, it will sit there safely with no problem. We're going to try to find the maximum additional mass that we can put at the very end and still have this be a safe situation. So that's my sketch, and the way that we're going to approach this is to use Newton's second law for rotational motion, which means that we add up all the torques that act on an object about some convenient pivot point or axis and set them equal to 0, and that will be our condition. So the important thing in this problem is to figure out where's the axis, what's the most convenient choice of the axis, and then what are the torques. So once we find the axis, we should be able to figure out how to draw the forces and therefore how to calculate the torques. Now to do this, we have to draw a force diagram, and rather than clutter up this sketch with more detail, I'm going to simply draw the beam over here, hopefully do a little bit better job than I did the first time. And now what we'll be able to show is where the forces are acting on it. Of course, there's going to be a force, and what I'm going to do is imagine the situation just as the beam begins to rotate. So just as it begins to rotate, here, let me redraw my sketch and see if I can make that a little bit better. Just as it begins to rotate, it will look like this. Here's the cliff. The left-hand side will come up off the edge, and I'm exaggerating it here, so that the only point of contact that the beam will have is right at the very edge of the building. And that's going to be a convenient place for us to calculate the torques. Okay, so first of all, we've got the center of mass of the beam, and we know that there's a force, the weight, pulling downward. The earth is pulling down on it. We also know that right at this contact point there's a normal force, okay, and I've exaggerated how much the beam is rotating. I really mean for this to be just as it begins to rotate. So it's still almost in a horizontal position, but there's a normal force there. And now we've got the additional force right, that is due to this unknown mass sitting at the right-hand end. So the weight of that mass is the force pushing downward on the beam. All of these are the forces that are acting on the beam. Okay, so what we need to do is write down the torques about the axis. And the axis that I'm going to use, as I mentioned before, is right at that contact point, right there. So if I do that, I can see that this normal force does not exert a torque because it goes right through the axis, and that makes things much easier for us. The two downward forces that remain that do exert torques will be labeled like this. I'll write down, since the one on the left, the weight of the beam itself, is the one that would tend to rotate it counterclockwise, I'll call that positive. And since the one on the right, the torque associated with M max, yeah, and let me get rid of the G there, because I really just mean for that to be labeled by which is the mass that's producing the torque. So those two torques, if we take the difference between them, they have to be equal to 0. Now what's the torque of the mass of the beam itself? Well, again, I've exaggerated this rotation, and so really the distance that I want is this perpendicular distance right here, which is between the center of mass of the beam and the edge of the building. And a little bit of simple arithmetic will show us what that is, because what we want, we know that this distance here, right, is L over 2, because that goes from the end of the beam to its center of mass, and the distance from the end of the beam to the edge of the building we drew was 2L over 3, right? And so what I want here then, I want to take the force, mg, times the perpendicular distance, and that is now, that's this distance right here. We can see that that's 2L over 3 minus L over 2. And I'll simplify that in a minute. But that's the force times this perpendicular distance that runs from the line of force to the axis. Okay? Now there's something similar for the mass on the end. This one's a little bit easier, right? Because the mass on the end has a weight that pulls straight down, and that's at a perpendicular distance L over 3 away from the axis. So that one's really easy. M max G times L over 3. And we subtract those two, set them equal to 0, and that's our condition for rotational equilibrium. All right? So now I'm ready to evaluate this expression and solve for M max. That is the unknown quantity. We want to know what's the maximum amount. If it's less than this maximum amount, then the beam will stay put. There won't be a net torque in the clockwise direction. Okay? But the condition right here is such that M max is just large enough so that the clockwise torque and the counterclockwise torques are equal and opposite. And making that mass any larger would cause the beam to rotate clockwise and fall off, as we've indicated in the lower sketch. So E, let's see, 2L over 3. So what we've really got here is mg. 2L over 3 is 4L over 6. We'll put these over a common denominator. L over 2 is 3L over 6, right? We've got that. And I'll just take the negative M max G L over 3 term and put it on the right-hand side. M max G L over 3. On the left-hand side, 4/3 4/6 minus 3/6 is 1/6. So this becomes mg L over 6 equals M max L over 3. Well, we see we can divide both sides by, whoops, no, don't do that. We can divide both sides by G, which apparently I was trying to do in my head. We can divide both sides by G, we can divide both sides by L, and those terms drop out, and then multiply both sides by 3, and we get that M max is exactly 1/2 of the mass of the beam. So we can assess this very quickly. We see, of course, It's got the right units. M max is a mass, and so we've got some fraction of the mass of the beam. So the units are appropriate for mass. And it's hard to know whether the value of 1/2 is reasonable, but we know for sure that if this mass at the end were the mass of the beam, it certainly would send it over the edge. So we kind of expect that the value for this maximum mass should be some fraction of the mass of the beam. So the value is less than m, which seems okay, seems reasonable. That's about all that we can say with this. So, just to review, we took a problem involving stability. We wanted to know what the maximum mass was for which this system would still be stable. It would not rotate and then fall off the building. So we applied Newton's second law for rotational motion and chose a convenient axis by thinking about the situation when it's on the very verge of rotating, when it just becomes unstable. So that led us to draw in the forces and then realize that although there are 3 forces acting on the beam, only 2 of them exert torques. We found the appropriate perpendicular distances. That's usually the most challenging part of these kinds of problems. And then just a little bit of arithmetic allows us to solve for this maximum loading mass that we can put at the very end. I hope this helps as you set up your homework problems, and I will see you in class.